So we left off last time hinting about slant asymptotes. They're called oblique asymptotes or they're called slant asymptotes. And what are they? Well, all they are asymptotes that you get that are not horizontal and that are not vertical. So they might be a linear equation like y equals 3x or y equals x plus 4. Instead of being a completely horizontal, completely vertical line, we have an asymptote that is slanted. Our function might behave in some way like this and like this, where our x and y plane might be over here. Now, I didn't give you the rational function that creates this slant asymptote. I'm just saying your slant asymptote might be in the form of these two. This guy right here. Could be either one, and it could be a negative in a negative direction. Your slant asymptote could be decreasing. That's where your values will approach but never reach. So let's do some example. How do you know when you have a slant asymptotes? Well, we stated earlier that slants or obliques happens when degree of numerator is 1 higher than degree of denominator. Now, why is that the case? Why is that you get a slant asymptote when the degree of the numerator is 1 higher than the degree of the denominator? Well, let's take an example. R of x equals x squared minus 4x minus 5, x minus 3. The numerator has a degree of 2. The denominator has a degree of 1. Well, remember what I told you guys, that fractions or rational expressions are just division of two polynomials at the end of the day. When you divide these out with long division or whatever, you realize that you're going to get a polynomial in the first degree. 2 minus 1 gives me something in the first degree polynomial. Now, it might have a remainder, but I'm going to get something in the form of maybe 2x plus 1, or it's going to be in the form of y equals mx plus b at the end of the day. It's going to be in the form of y equals mx plus b. It's going to be in that form. So when I actually divide this out, I might get a remainder. So I might say plus r. A remainder. Oh, this is confusing because we use r for our function. Let me use capital R. Remainder. So to calculate slant asymptotes, the idea is that we're actually just going to divide it out, and then we're going to get a linear function with some remainder. Our remainder might not be 0, but if it isn't 0, if we do have a remainder of non-zero, that means I will have a slant asymptote. So let's observe some functions. Let's observe this one actually. So already when working on sketching the graph or anything like that, you should have factored it out. This is something we have to do routinely when we're working with rational functions because it just helps us find all of our key points. So if I factor out the numerator, I get x minus 5 times x plus 1, I believe. Yep, that checks out. All over x plus 3. Now, to calculate the x-intercept, remember, it's the zeros of your numerator, because 0 divided by any number, any fraction, 0 as your numerator, will have your entire fraction equal to 0. So it's equal to 5 and negative 1. Those are your x-intercepts. Your y-intercepts, well, you have to plug in 0 for x. So what is r of 0, which is going to be negative 5. This is a 1, and this is a 3. Negative 5 times 1, that's negative 5. Divided by 3, that's negative 5 over thirds. All right, this is nice having our function in factored form because we can do calculations much quicker, like how I just did it. All right, so we got our x and y intercept. Vertical asymptote. Well, that's the zeros of our denominator, and notice nothing cancel out, so I don't have any missing holes or anything. So my zeros is going to be x equals negative 3. That's my vertical asymptote. Now, horizontal asymptote. We should have none because the degree of my numerator is bigger than the degree of my denominator. If I did long division, I would have a polynomial. Maybe it might have a remainder, but I'll have a polynomial of degree 1 or higher. So that means I have no horizontal asymptote. But because the degree is higher than 1, it is 1, I'm sorry. The degree is 1 more than the denominator. I am going to have an oblique asymptote. So let's do long division out. If you were to do long division on this guy, if you recall how to do long division, x squared minus 4x minus 5. Long division of x minus, is it minus 3? Yep, minus 3. You check the degrees. Then you get your leading coefficients. Oops, this is not degrees. Get your leading coefficient. That's going to be x. X times x would give me x squared. Now I distribute this across. I get x squared minus 3x. And we're subtracting. These cancel out. This turns into a plus. We get negative x. Drop the minus 5 down. And then we can put minus 1. Because minus 1 times it. Distribute this guy over. We get negative x plus 3. And then we get x minus 2. Oops, is our remainder. Oops, not minus 2. Negative 2 is our remainder. So this is going to be minus 2 all over x minus 3 as our remainder. Remember, we write our remainder as whatever our leftover is over our divisor. That's how we write it down. So you get this piece right here. This is our quotient. However, the important part of our quotient for graphing it is actually the non-remainder part. So we say our oblique asymptote or our slant asymptote. I'm going to call it slants because that's more intuitive. Slant asymptote is at x minus 3. Y, oops, not y equals x minus 3, I'm sorry. Y equals x minus 1. That's where our slant asymptote is located at. The remainder doesn't really have to do anything with our asymptote, thankfully. It just tells us that, hey, when I graph it out, it's actually going to have an asymptote. If it divided out cleanly, that's a different story. So now when I graph this guy, I have an idea. Of course, I have to check my behaviors and everything. My functions will approach this value, but I have to check my behaviors of my vertical asymptote. We always have to do that. The left side of our vertical asymptote, the right side of our vertical asymptote. All we did with our horizontal asymptote is that's where our function will approach at the very end, so we don't even need to do a table. That behaves the same way with our slant asymptote. We just need our function to be approaching it. So let's do a table. Let's do our function. Let's recall r of x equals x plus 1 times x minus 5 all over x minus 3. If I did a table for that, let's do x approaches 3. Is it plus or minus 3? Let me just check just to be sure. It is, did I do this wrong? Oops, this should have been on minus 3. So that means our vertical asymptote was plus 3. I apologize for that. So we're going to check 3 from the right, and then we're going to check 3 from the left. From the left. This is our table that we're going to draw. Now, we're going to let x equal, let's say 3.01. We're going to let x equals 2.99. Okay? Let's plug that in. So we got to check our sign. Our sign. Sign. Well, if I plug in 3.1 to the first factor, that's going to be positive. If I plug it into the second factor, that's going to be negative. All divided by, if I plug it into the denominator now, that's going to be positive. And then for the second one, if I plug that in to the first one, 2.99 plus 1, that's going to be positive clearly. If I plug into the second one, that's going to be negative. However, when I plug it in my denominator, that's going to be negative. So the final column that we should do, what is our sign? Well, y has to approach, in this case, it's going to be negative. Infinity, I'm sorry. Let's put in negative infinity. Because positive divided times a negative, that's a negative divided by a positive, that's still a negative at the end of the day. On the second one, however, positive times negative, that's a negative divided by a negative, should give me positive. So, roughly, my function Why did it draw it so weird? I'm going to delete that. Shape. Let me zoom out real quick. Let me use a different color. Oh, I could change colors here, actually. Let's change this color. I like this color. Oh, I didn't change color. Oh, well. Well, now when I actually draw my function, the vertical asymptote was at 3. 1, 2, 3. So I draw a dotted line. This is my vertical asymptote. X equals 3. And then I can draw my slant asymptote. It's the function x minus 1. We should know how to graph that. Your slope is 1. Your y-intercept is negative 1. So there's a point here. And then we draw our slope, which is 1. So this is my slant asymptote. Let me use purple to denote my slant. Apologize for that noise. But boom. This is my slant asymptote, which is x minus 1. Y equals. Boom. So now I got to draw my function. Well, I know that my function never touches these asymptotes, but on the left side of 3, my vertical asymptote x equals 3, I should approach positive infinity. So I should blow up all the way here. But I can't touch my slant asymptote, so I have to go down like this. And on the other side of x equals 3, well, now this is when it gets a bit weird. It says here it goes to negative infinity, so I have to start from down here. Well, then now I have to go eventually to my slant asymptote. So boom. This is how your function should look if you graphed it correctly. Now, why did I not graph it in this area? Why did I not graph it in this area? Well, the reasoning why your function is not located in those regions is because those regions are for y approaches infinity in this case, y approaches negative infinity for this case on the left side and on the right side respectively. So that is the reason why I was able to choose which side to graph based on the behavior as y approaches for my vertical asymptote based off of these guys. And that helps us out. So that's slant asymptotes. So I do expect you guys to know how to graph slant asymptotes. Now we move on to the final subject for chapter 3. 3.8. Solving rational inequalities. Now the good side, you don't even need to graph this. To solve rational inequalities, you do not need to graph it. Now, it does help having a visual demonstration of it, but it's not necessary. We can do it algebraically. I don't expect a sketch every single time. When you get to calculus, you will be sketching, but I don't expect a sketch every single time. So, solving rational inequalities. So the first thing you need to do, I'm just going to give you a few steps, is for any sort of inequality, you know, generally we can solve it normally, but then when you're doing rational inequalities, the main thing we have been working with is zeros. This concept of zeros, when we factor it out, it plays out nicely if we can solve for our zeros of the numerator and zeros are for our denominator. So it only makes sense that set inequality equal to 0. Equal to 0. I mean, not equal to 0, I'm sorry. Set inequality to 0. It's not an equal sign, that's why. It could be a less than symbol or a greater than symbol. It could be a less than and equal to symbol. It could be a greater than or equal to symbol. Just set one side to 0 is my main argument. And then we follow the same rules, and then I'll add on to more pieces with this, all right? I'll add on to more. We know we have to factor, though. So we can just say that. Let me give you guys an example real quick, though. Let's say I have r of, or let's say I'm not even going to use a function now. Now I'm solving an inequality, not a function. But I can treat it as a function if I wanted to. 1 over 2x minus, or over x squared minus 2x minus 3 is greater than or equal to 1. This is hard to visualize, or hard to even work algebraically. So what we need to do is get rid of this 1. Because if I try to set the numerator equal to 0 to find my x-intercepts, then it doesn't work because it's not equal to 0. It's greater than or equal to 1 at the moment. So we need to fix that. So subtract 1 to both sides. So if we subtract 1 to both sides, minus 1 is greater than or equal to 0. Remember, I didn't divide by negative at all, so I'm perfectly fine. Well, you should see an issue with this already. Already, I don't like the way this looks. I would love it if we had one rational expression instead. So go ahead and combine them together. Well, if I wanted to combine them together, this is just 1 minus 2x over x squared minus 2x minus 3 minus, and then I just times my denominator out because it's just 1 now, right? So I can do that. So I'm going to drop my stylus, but I can multiply it, and it's just, this is just x squared minus 2x minus 3 all over x squared minus 2x minus 3. Because it's just 1 at the end of the day, negative 1 is greater than or equal to 0. I still didn't multiply or divide anything by negative, so I do not have to switch direction of my inequality. Now I can actually move them together. So now I have 1 minus 2x. Now, I'm actually going to change subtraction. I don't like subtraction, so I turn it to addition. But in doing so, I have to change the sign of all of my numerator. So this first term becomes, let me use a different color, negative. The second term becomes positive, and the third term becomes positive. If I do that, I have exactly minus x squared plus 2x plus 3 greater than or equal to 0 all over. Now I'm going to factor this guy because I like my denominators to be factored, generally speaking. So we're going to factor as x minus 3, x plus 1. Now the reason why I did not factor earlier on is because I needed to multiply and combine like terms for my numerator. You need to eventually combine like terms for your numerator, so that means you got to distribute. So why waste time at the moment when you can factor later on? So, because look at this, I have to combine these now. Well, if I combine these together, I get x squared minus x squared. The 2x cancels, the 2x and the minus 2x, they cancel out, thankfully. They're like terms. And then I have plus 4 all over x minus 3, x plus 1 is greater than or equal to 0. But wait. This, I don't know how to factor that. I don't. I do know how to factor x squared minus 4, though. What's the difference? Well, if you notice, the signs are different, which means, what if I were to instead factor this out by negative 1? Then when I would have exactly what I desire, so I can factor it out nicely. This is all just to make the problem much nicer to work with, okay? And then you have negative 1, x minus 2, x plus 2, all over x minus 3, x plus 1 is greater or equal to 0. I still didn't multiply or divide anything by negative 1. I factored, but I didn't divide. This is why I say division is not the same thing as factoring. You have to be careful. You're still keeping that term, or you're still keeping that, I guess, factor with you. All right, so now we have this problem. How in the heck do I know what my solutions are? Because an inequality has infinite amount of solutions at times. It can have infinite amount of solutions. I just need to know what region. Well, the best way to think about it is that when we talk about any sort of rational functions, greater than or less than or equal to 0, let's suppose we're talking about greater than or equal to 0. We can have a rational function like this. Oops. This is not our graph, but I can have a function that looks like this. Remember, rational functions do not need to be continuous like a polynomial function. They don't have to be this idea of connected. I'm not going to say what connected is because that's very loose. But do you see these functions? The problem is not just one piece is above our y value 0. If you notice, the ones that are above zeros are everything here. Oops. Are the pieces, let's say this is our vertical asymptote, are all the pieces here to here. Well, this x-intercept, I can't mess this up because the moment I cross the x-intercept, I'm going to be below 0. So these ones don't work. These ones don't work. But then, I'm sorry, can you fix that up? These ones don't work because they're all below 0 for the y value, part of my function. But then if I pass my next vertical asymptote, it does work for all the regions. But then if I go to the left side, none of them works for any part that's to the left side. So I need to know these important parts to determine if it's greater than or less than or equal to 0. I need to figure that out. So that means I need key points. We call this CP for cut points. Where is my polynomial, or where is my rational function being cut up into different regions? If I can find those cut points, I guess regions for rational functions that are key. There could be a better definition, but this is my loose definition. I don't even think the book gives you a definition. It might, but so the cut points. What are the important pieces for our cut points? They are going to be your vertical asymptote. Sometimes it's separated by vertical asymptotes. It's also going to be where your x-intercepts are. These are the main two parts for your cut points. Your vertical asymptote and your x-intercept. My vertical asymptote will tell me, hey, on this side is true for everything on this side until I either hit another x-intercept or I hit another vertical asymptotes. If I hit those, the behaviors might change, because if I hit the x-intercept, clearly I'm either being positive or negative, but I'm changing. Unless I bounce, of course. But that's the idea. So that's when you can either be above or below 0. You either have to identify your regions of interest. On the left side of the vertical asymptote, on the right side, did it pass an x-intercept? Did it not pass an x-intercept? But how do we do this? With this problem that I just gave you right here, how? Well, think of it like a number line. My points of interest are going to be my vertical asymptote and my x-intercepts. The vertical asymptotes are the zeros of your denominator. The x-intercepts are the zeros of my numerator. So I'm finding the zeros of my numerator and the zeros of my denominator. Those are the key point that identify these regions, that separate these regions in particular. So I need to know my vertical asymptotes. So it's going to be x equals, that's for my term, 3 and negative 1. And then my x-intercepts are going to be 2 and negative 2. If I plot this here, negative 1 is over here. And then, oops, I should have done this better. Let's suppose instead this was negative 2. I don't need this piece. Let's call this piece negative 1. Let's call this piece 2. Let's call this piece 3. I need to know which part for my problem is above, greater than or equal to 0. So I have to check each region of interest manually. I have to check this region. 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 And I have to check this region. So I have to choose test points for each one of these and see if they are going to be greater than or equal to 0. So let's go ahead and do that. Well, in particular, let's make a table. Table similar to how we did our rational functions. Let's start off with negative 2. Then we'll go to negative 1, and then we'll do 2, and then we'll do 3. This is our CPs. It's very helpful if I write my function up here so we don't forget what our function is. Negative 1 times x minus 2, x plus 2, all over x minus 3, x plus 1. X minus 3, x plus 1. This is our function, so we don't forget. So now I have to choose test points. Something to the left of each of these values, or something to the left and something to the right of each value. So let's break this up even further. This is to the left, negative 2 to the left, negative 2 to the right, negative 1 to the left, negative 1 to the right, 2 to the left, 2 to the right, 3 to the left, 3 to the right. And in particular, I'm going to use values x equals. For the first one, I might use 2 to the left. That's a number such as 2.001. Negative 2 to the right. That's like negative 1.999. Negative 1 to the left, that's going to be values like negative 1.001. To the right, negative 0.009. Oops, I'm sorry, not 009. 0.999. 2 to the left, positive 2 to the left. Positive 2 to the left, which is going to be 1.999. 2 to the right, 2.001. 3 to the left, which is 2.999. 3 to the right, 3.001. These are going to be our test points that we're going to use. Now I need to see the sign of my function. Is it going to be positive? Is it going to be negative? All right. So if I plug these values in, and of course you're not going to get 0 because these are decimals that we're working with. And our rational function does not have those decimals. But if I plug these values into it individually, so the first thing you notice is that, hey, I have a negative. Put a negative in the numerator already for all of them. Account for that guy already. All right. Now we do the next one. If I plug in negative 2.001 to the first guy right here, minus 2, well, that's a more negative number, so I get negative for that piece. Now, if I plug it into positive 2, well, this negative number is bigger in magnitude. It's when we think of it intuitively, it is bigger. It's just more negative. So we're going to say this is actually still negative on top. So we have 3 negatives on my numerator for the first one. If I plug into my denominator, well, that has to be a negative if I subtract a value. And then now negative 2.00 is bigger than 1, so we're going to say it's negative here. So boom. I have all negatives for my first sign. Now, for the right one, for the next one, 2 to the right, negative 2 to the right, if I plug that in, then negative 1.9, I should still get negative because we're subtracting. But now that I'm adding, this actually turns to positive. All over, this has to be negative. This has to be still negative because negative 1.99 is bigger than, or it has larger size than 1. I use the word magnet. I want to use the word magnitude, but I haven't introduced that just yet. And if I do the third one, we can actually fast forward this all the way to, let's see, this is negative. This one right here is positive. All over, what is that, negative? And then I have still a negative. But then if I move over here, I have negative. I have negative. And you'll get the hang of this. This will become much quicker, or this will turn positive, sorry. You'll get the hang of doing these much faster. And then the denominator is negative. The other denominator part is positive. 1 is bigger than that number from the distance from 0. And then the next one, well, this one right here is going to be negative. 2 is bigger. And then the next one's going to be positive. And then 1.99 minus 3, that's going to be a negative number. But then if I add 1 to it, that's definitely going to be positive. Keep moving forward. 2.001, that's going to be positive actually. Then this stays positive over here. And then this is going to be negative. And then this is going to be positive. And moving on to 3 to the left side, this guy is positive, but this guy is still positive, of course. Sorry about that. And then if I move downwards, this is negative, and this is positive. But then on the last one, I have, what is that? Positive, positive, all over, positive this time, and positive. They are almost all positive except for that initial negative 1. Now, I have all of the, I know the sign of it. So now let's actually calculate to see if they're supposed to be positive or negative at the very end. So negative times a negative times a negative divided by a negative divided by a negative. What is that? Well, there's a negative times a negative, that's positive, times another negative is negative. Divided by a negative, it's positive. Divided by another negative, it's negative. Oops, let me just write negative at the very end. So this is the result. Let's call this one right here. This is the sign. This is the result. The resulting one. Let's make another row for this just to make it clearer. This right here is going to be negative at the end of the day. Over to the next one. Well, I drew this incorrectly. Fix this up. There should be a negative. So negative times a positive divided by negative divided by negative. That's positive. If I keep going, let's see. Negative times a negative, positive, positive, positive. There's only one positive on there. If I keep going, negative times a negative, that's positive, times a positive, which is positive, divided by a negative, which is negative, times a positive, which is negative. And then we keep going. Positive, negative times negative, positive, times positive, it's positive. And this has to be negative. I'm kind of zooming in now, going a bit faster. This is positive because there's two negatives. This right here is still positive, and the last one is negative. All right, so we have the signs. Why are they useful? Well, I needed to know if they were going to be greater than or equal to 0. So if they're positive, I check out. All right, if they're positive, I check out. Which ones are positive? Well, 2 to the right is positive. Negative 1 to the left is positive. What else is positive? 2 to the right is positive. Negative 3 to the left is positive. So those are our intervals. So if I wanted to do my interval, I would say that I want negative 2, negative 1, and then I think it was 2 and then 3. In particular, I want all the values on this side. Now, I can't have both of them. I can't include 2, mainly because I can't. I'm sorry. Fix that up. I actually want all the values that are positive. So I want this section right here. Boom. I apologize for that. Now, that's where 2 from the right and negative 1 from the left is. I want all those values. So this is the piece I want. Right here. Now, do I include negative 2 or do I not include it? Well, the right side of it is positive, so that does work. But the left side doesn't work. So I actually do an open circle at negative 2. Now at negative 1 on the left side, negative 1 on the left side works. Great. But what about negative 1 on the right side? It does not work. So I have to do an open circle here. Now the next parts that work is 2 from the right to 3 from the left. So I want this section right here. Boom. Now do I include 2? Well, look at 2. 2 from the left is negative, 2 from the right is positive. If they're not both positive, then I have to have an open circle. If they're both positive, then they both satisfy my inequality, so I do a closed circle. But in this case, this is also an open circle. And then let's see, these are my actual only interval. 3 from the left is positive, but 3 from the right is negative. So I can't include that as well because I don't have both positive. So this is the interval I actually want because 3 from the right is also negative. These are all the ones that are going to be greater than or equal to 0. So in particular, in interval notation, the solution x belongs in this interval negative 2 all the way to negative 1 union 2 to 3 parentheses. Use parentheses if you do not want to include. If it's an open circle, parentheses. If it's a closed circle, then you color it in, use brackets. Now, this depends on the direction here. Because I want positive values, I'm only looking for positive 1. If it was less than or equal to 0, I would have to do the reverse. All right? And if I did less than or equal to symbol, let's see, does any of them actually play out nicely? Nope. We have 3, 2, 1. Nope. So, and even in our negative cases, even if we use less than or equal to 0, then we still will have open circles for all of them because they would need both negative to be satisfied. In our case, we need both positive for the left and right side of our CPs, of our cut points. So that's an idea. And if you want to visually draw this, you already have your asymptotes that you can draw. You can draw your asymptotes and whatnot. And then after you draw your asymptotes, or you know how it behaves on the asymptotes already. So let's say your asymptote in this case was positive 3 and negative 1. Positive 3 and negative 1. Positive 3 is over here and negative 1 is over here. You have a vertical asymptote. And then to the right side of 3, in particular, it's negative. So that means I have, or do I have a horizontal asymptote? Let's check. What's the degree of the polynomial? The degree of the polynomial, oh, they're both the same actually, aren't they? Yeah, they have the same exact degree. So that means I have to check the ratio between them, which would be -1. The leading coefficient here is -1. The leading coefficient here is just 1. So that means it's -1 where my horizontal asymptote is. So I have a horizontal asymptote at -1. Now I can actually draw it out. I do not have a slant because the degrees are equal. So now when I draw it out, to the right side of +3, I want to say +3, the right side of +3 is negative. So I go to -infinity. And I have to go to my end behavior. Boom. And then if I wanted to do to the right of 3, to the left of 3, I'm sorry, it's positive. To the left of 3 is positive. So it goes to +infinity. I can't touch my horizontal asymptotes, of course. Then I go to the next asymptote, which is -1. -1 to the right side is negative. So somehow I have something like this. And then to the left side of -1, it is positive. So I have something like this. Boom. And then I should have my function now. Yep. Those are it. And this is how my function behaves. Some weird behavior. I don't know exactly, but it has this kind of weird behavior. Boom. And that leaves it for solving rational inequalities. You need to be able to use this table right here, the left and right side of all your cut points. In calculus, you would call them critical points. In our class, we call them cut points for now because we're not doing derivatives. But you have to get all of your cut points with your vertical asymptotes and your x-intercepts, and then figure out if they're going to be positive or negative based on their signs. Well, I did not plot the x-intercepts, did I? My x-intercepts are 2 and -2. Let's plot those out. 2 and -2. 2 is all the way over somewhere around here. Oh, so it touches here. And then it levels out. And then -2, somewhere around here. So the graph is more accurate if I draw it this way. Boom. And then it has to touch it over here, so it's more accurate if I did this. Boom. Something along those lines. All right, so that leaves it for chapter 3.7. That's all of chapter 3 we have covered. And make sure you guys do the discussion board that are posted for my online class. Because I have yet to see anybody start it, but it takes a long time to actually do that. Because one of the polynomial isn't nice. It has, I think, 5th degree, and you have to plot all of its x-intercepts or roots, which means that you have to do you have to do 5 successful synthetic division, or at least I guess 4, because you can leave it as a quadratic. You have to do 4 successful synthetic division. That's the minimum amount you need to do. All right, so take care. Have a good day.